Professor Adam Ree, a Nobel Prize winner, warns of a strange discovery that the James Webb Space Telescope has made, indicating that our understanding of the universe was completely wrong. The universe is expanding in a way that we no longer understand, and Webb shows us galaxies that are so strange that they are actually impossible. What some see as a failure across the board is for researchers like Ree the beginning of a new science that brings long overdue answers to elementary questions about the universe. Ree believes that the expansion of the universe and Webb's crazy observational data are connected, and perhaps the whole crisis is down to one tiny detail that we have simply overlooked so far. Even the old Hubble Space Telescope had shown us a strange image of a complex galaxy that is unusually old. The galaxy, called GZ9P3, was for a long time just a blur of light, and we could hardly find out any more details about it until Webb came along. The new telescope not only confirmed the existence of this galaxy but also its unusual age. GZ9P3 existed only 510 million years after the Big Bang, making it a galaxy in the relatively early stages of the universe, which is thought to have begun 13.8 billion years ago. GZ9P3 has now been thoroughly investigated by the International GLASS project, and more inconsistencies have come to light. GLASS, which stands for GISM Lens Amplified Survey from Space, searches for the light of the oldest galaxies in the universe. The results showed that GZ9P3 was not only unusually advanced for its age, but also very likely the result of a merger between two or more smaller galaxies. This, like the existence of the galaxy itself, is a scientific miracle. 510 million years after the Big Bang, finished galaxies may theoretically have already existed, but they are unlikely to be as developed and large as GZ9P3. The fact that galaxies have already merged at this early point in the universe turns our old theories of galaxy evolution on their head. The new study by the JWST also shows that GZ9P3 has a double nucleus, indicating that the merging of the galaxies could still be in full swing at the time the image was taken. The GLASS team discovered that GZ9P3, similar to other early galaxies observed by the JWST, is already so massive and mature that its appearance is unusual for galaxies in the young universe, to say the least. Many researchers today are talking about the impossible, although we must be careful here because these galaxies clearly exist and are therefore not impossible. Rather, it's simply impossible for our science to explain their existence in terms of our cosmological models. These galaxies already contain several billion stars in this early epoch, and yet we are in the era of the end of the Dark Ages, which means that only the first stars should actually be visible. James Webb was constructed and launched into space for the purpose of showing us exactly these early stars, but instead of the first protostars and loose clusters of galaxies, we see impressive and highly developed galaxies that look as if they are already several billion years old. How can these galaxies exist? What many people didn't know is that Hubble had already discovered a number of very old galaxies that didn't quite fit the picture back then. At that time, galaxies that existed 500 or 400 million years after the Big Bang were regarded as individual exotics and special cases. Additionally, it was not entirely clear whether the light spots were actually complex galaxies, as Hubble's images were nowhere near as informative as James Webb's images are now. Bright and luminous objects in the early universe could also have been clusters of the famous population 3 stars, said to have been the very first stars in the universe. These stellar giants had a luminosity that would make today's stars look pale, but they burned out after only a few 100,000 or million years. Now we know from Webb's analysis that there are millions or billions of stars within these blurry-looking patches of light, which does not fit with the old assumptions of a few giant stars clumping together to form protogalaxies. Many of the galaxies examined by Webb already show complex structures such as spiral arms and bars, which also speaks against a young developmental stage of the galaxies. However, GZ9P3 is a real mystery among the very old galaxies discovered so far for other reasons. It's not only more massive than expected but also about 10 times more massive than other galaxies that the Webb telescope has seen in a similar epoch of the universe. The complex shape with 2 bright spots revealing dense cores suggests that GZ9P3 probably formed when 2 early galaxies collided. In Webb's detailed images, a large number of young bright stars were visible within GZ9P3. This young bright stellar population was probably formed by the galaxy merger and is less than a few million years old. Within the galaxy, Webb also found an old stellar population that is already over 100 million years old. The GLASS scientists used Webb's advanced spectrometer to uncover all this fascinating information about this extremely distant galaxy. It's fascinating what we can now discover today thanks to our technologies. Being able to observe details of a galaxy more than 13 billion light-years away is a great stroke of luck for our cosmologists. With the help of Webb spectroscopy, we can even determine the elements that make up these stars. Since young and old stars have different compositions, the researchers were able to separate the two categories in this early galaxy. Older stars usually appear redder and are richer in heavy elements, which astronomers also refer to as metals. If old stars have largely burnt up the hydrogen supply in their cores by fusing it all into helium, this helium is then burnt, and even heavier elements are produced. Younger stars, on the other hand, are still dominated by hydrogen and some helium and are thus clearly separable from the older stellar populations. For Webb, GZ9p3 is rich in silicon, carbon, and iron, the latter being the heaviest element that can be synthesized by stars. This means that when these stars died in supernova explosions, they would have enriched the early universe with metals. Much of this metal content would later have become the building blocks of the next generation of stars, our galaxy, the Earth, and ultimately ourselves. Adam Rees states that we have misunderstood the universe. It's a fascinating fact that the best telescope in the world, the James Webb Space Telescope, confronts us with so many new facts, forcing us to completely rethink cosmology. Adam Rees, the Nobel Prize winner and researcher at Johns Hopkins University in the USA, has been researching the so-called Hubble tension for a long time. He realized before Webb's launch that we probably had a glaring error in our previous understanding of the universe. Rees is one of the leading scientists researching the Hubble constant, the rate at which the universe expands. Scientists have used this constant to determine distances, expansion speeds, and also the age of the universe. Rees and his team researched the discrepancy in the measured values for the expansion rate, which occurs when the measurements are fixed at different points. Measuring the universe and dynamics within the universe is not easy because all objects are in constant motion, and we have no walls of space that we can use as measurement constants. So scientists base their measurements on the objects and events that are considered to be the most constant, and these are usually phenomena that emit a lot of light. Light is considered to be the most reliable quantity in the universe. However, light is also in constant motion. Another source is the cosmic background radiation, which resembles an imprint of the earliest events in the universe. Measurements of expansion based on cosmic background radiation have shown an expansion rate of about 67 kilometers per second per megaparsec, while research based on data from seeded stars has shown a rate of about 73 kilometers per second per megaparsec. Adam Rees and his team were able to refine their work thanks to the Webb telescope and wanted to find out whether a potential measurement error of the Hubble Space Telescope could be the cause. But Webb showed the same deviations, which is worrying. Somewhere between these two observations, there must be a fundamental flaw in our understanding of the universe, said Rees in an interview with the Astronomical Journal in the USA. The use of the new space telescope has allowed us to look deeper into the universe through its sharp infrared view and to study cosmic distances even more precisely. Now that we know that Hubble and Webb confirm the significant deviations, we can be sure that there is an error. For Adam Rees and his team, this is a step forward. If measurement errors can be ruled out, we need to look into our other thought constructs and theories to see where the error is hidden that can explain all these strange observations and apparent impossibilities. Since Webb took up its post, the discoveries that are not compatible with our old theories have been piling up. Adam Rees, who was awarded the Nobel Prize in Physics in 2011 for discovering the accelerated expansion of the universe, sees these findings as an opportunity to advance science. If our previous measurements of the universe are not correct, the determination of age, the idea of expansion, and even the idea of a Big Bang could be wrong or at least not quite right. The universe may be much older than previously thought, and these discoveries even have implications for the history of the origin of matter. Unexpectedly massive and highly evolved galaxies clearly indicate that the universe 13 billion years ago and more was not what we previously thought. New perspectives on the universe prompt us to question our understanding. When a scientist like Rees claims that our picture of the universe is probably completely wrong, thoughts of an infinite universe, the crazy dimensions of string theory, or the possibility that there are millions of universes according to quantum physics might arise. Scientists are currently still vehemently refusing to open the door to theories such as the quantum universe based on the new observations. Instead, they believe that the deviations in the Hubble constant could be due to misunderstandings or misinterpretations of dark energy. This mysterious force, which is understood to be the driving factor behind the accelerated expansion of the universe, is largely unknown in terms of its properties and behavior. It could be, for example, that dark energy is not evenly distributed throughout the universe or that its effect changes over time and space, leading to the different measured expansion rates. Another line of thought could concern the equally mysterious brother of dark energy, dark matter, which is another important component of our ancient cosmology. However, we have never been able to prove its existence and thus its true properties. Perhaps we overestimate its uniformity and underestimate the complexity of its distribution in the universe. Irregularities in the distribution of dark matter could influence the cosmic structures and the observed expansion rates in exactly the same way as we are currently experiencing. The quest to understand the universe's mysteries has often been a journey of unexpected revelations and paradigm-shifting discoveries. At the forefront of this endeavor stands Professor Adam Ree, a distinguished Nobel laureate whose work has illuminated the cosmic tapestry in ways previously unimaginable. His insights, particularly through the lens of the James Webb Space Telescope, JWST, have fundamentally challenged our foundational understanding of cosmic evolution and the nature of galaxies. Ree's pioneering research, focused on unraveling the enigma of the universe's expansion and the discrepancies within the Hubble constant measurements, has unveiled profound complexities. The JWST, with its unprecedented capabilities in infrared observation, has not only corroborated earlier findings, but also unearthed galaxies that defy conventional astrophysical theories. These discoveries, exemplified by galaxies like GZ9P3, pose fundamental questions about the early universe's dynamics and the processes that govern galactic evolution. Galaxies such as GZ9P3, emerging a mere 510 million years after the Big Bang, challenge the notion of a gradual and uniform cosmic evolution. Their existence suggests that galactic mergers, typically associated with later cosmic epochs, were surprisingly prevalent in the universe's infancy. The dual nucleus observed within GZ9P3 hints at a tumultuous cosmic history, where collisions between protogalaxies could have triggered rapid stellar formation and structural evolution on a scale previously unimagined. The implications of these findings extend beyond theoretical astrophysics into the very fabric of our understanding of cosmic origins and evolution. If galaxies like GZ9P3 were already formed and merging in the early universe, it calls into question the timeline and mechanisms of galaxy formation models. Traditional theories, positing a gradual buildup of galaxies over billions of years, may need to be reevaluated in light of these anomalous discoveries. Moreover, the intricate spectroscopic analyses conducted by the GLASS project have revealed rich details about GZ9P3's stellar populations. The presence of both young, luminous stars and older, metal-enriched stars within the same galaxy paints a complex picture of its evolutionary history. This dual stellar population not only challenges existing models of star formation, but also provides crucial insights into the early enrichment of cosmic metals and the subsequent formation of subsequent generations of stars and planetary systems. The role of James Webb in these revelations cannot be overstated. Designed to peer deeper into the cosmos than ever before, Webb's advanced instruments have enabled astronomers to study distant galaxies with unprecedented clarity. By analyzing the elemental compositions of stars within GZ9P3 and other early galaxies, scientists can trace the cosmic lineage of heavy elements essential for the formation of life as we know it. Beyond its contributions to astrophysics, Webb's observations have profound implications for our broader understanding of cosmology and the nature of the universe itself. The discrepancies in the measured values of the Hubble constant, as observed by Webb and earlier telescopes like Hubble, hint at underlying complexities in the universe's expansion dynamics. These discrepancies challenge us to refine our cosmological models and theories, pushing the boundaries of human knowledge further into the unknown. Adam Ree's pioneering spirit in tackling these cosmic puzzles reflects a deep-seated curiosity about the universe's inner workings and our place within it. His insistence on questioning established paradigms and embracing new observations as catalysts for scientific progress underscores the essence of exploration and discovery. In the face of these challenges, Rhee and his peers advocate for scientific rigor and open-mindedness, recognizing that each new discovery brings us closer to unlocking the universe's most profound secrets. As we stand on the precipice of a new era in observational astronomy, propelled by Webb's capabilities and the ingenuity of future space missions, the cosmic landscape beckons with tantalizing mysteries. From the depths of dark matter and dark energy to the origins of the first galaxies and the possibility of multiverse theories, the universe continues to defy our expectations and expand the horizons of human understanding. In conclusion, the journey of discovery catalyzed by Webb and championed by visionaries like Adam Rhee reminds us of the boundless potential of human curiosity and scientific inquiry. With each new revelation from the cosmos, we inch closer to a more comprehensive understanding of our cosmic origins and our place in the vastness of the universe.